Okay, but moving right along, we're going to talk about parametric equations today. Here's a slide where we kind of like introduce this idea of parametric equations. What are parametric equations? How are they different than the regular equations we've been working with? So before, we usually graphed things that had one equation and essentially two variables, an x and a y. Now, we know that we could change those variables, like maybe if we were doing exponential growth or decay, we might change our x to t because it represents time. But essentially, we were just doing one equation with two variables. Okay. Now, in this section, we're going to introduce a third variable. And that third variable usually represents time or an angle, and that third variable is called your parameter. So you're introducing a third variable. You will still have x and y. You will have a third variable that is your parameter, usually time or angle, depending on which you'll use t or theta. And in order to introduce that third variable, that means that we are going to have two equations, one for x and one for y, which is what we would call the parametric equations. Now, you'll have an equation for x in terms of t, or as a function of t, so x depends on what t is. Then you'll have a second equation for y, which also depends on t. So it's a function of t. Both x and y variables will be a function of t. Now, parametric equations, the ones that some of the ones that we'll see today in our homework and in our examples, are actually functions that we have already seen and worked with before as just like plain old rectangular equations with only x and y. So I'll try to make some connections when we're graphing different parametric equations in our notes today. Like this is like that function that we did, back in semester 1. This was how we would have graphed that function. See, we're getting the same thing. Okay, so there are some connections that you can make there. Now, the rest of this slide is an image from your textbook in section 10.6. I do not think that you need to copy anything from the image down into your notebook. I think just kind of like pay attention to like what we're looking at, what's going to be different about the graph of a parametric equation. So this is an image in that section of your textbook where we have a curve that is being graphed. And over on the side here, we have two boxes. One of those boxes is the rectangular equation. So this curve is really y equals x squared divided by 72 plus x. That's a graph we could graph from our previous knowledge. Like we already know a lot about that function. It's quadratic, so its shape is a parabola. It has a negative a value, so it should open down. Okay. And the c value is 0, so it should have a y-intercept at 0. We could do some other things like maybe factoring to solve to find x-intercepts. We could do like opposite of b over 2a to find the vertex. So we have a lot of knowledge already about quadratic equations. And what you see over here on the right, like that looks like the graph of a parabola, right? That opens down. Okay, so it's agreeing with our rectangular equation. Now, that equation can be written as a set of parametric equations that are in terms of the variable t. Okay, so here we have our parametric equations in terms of the variable t. Think about what that means, that third variable. Remember, it usually is time or an angle. So in this particular example, we're probably saying time. And I could build a whole story around this graph of parametric equation. Like suppose I was a person and I'm kicking a soccer ball, okay, from the ground. Okay. The graph that we see, we've got an x and a y axis. We can determine the horizontal distance of the soccer ball. We can determine the vertical height of the soccer ball. And by writing it as a parametric equation and including this parameter of t, I now know extra information that you can see like listed here at t equals 0, at t equals 3 square root 2 over 4, at t equals 3 square root 2 over 2. Okay. I now know when it was that far away from me horizontally, or when it was that height vertically. Okay. So previously, we could maybe sometimes have a t value with it, like a projectile motion, but then it would be like just t and y. Okay. And we wouldn't also have the horizontal distance. So we'd have like time and vertical height. Now we have horizontal distance, vertical height, and the time. Okay, so we have all three of those values. We have more knowledge. The other thing that I want you to take a careful look at, you know, like what's different from this graph besides like having maybe like being able to label the t values. The other big difference that you're going to have to focus on when you're doing your homework and your test next Wednesday, there are arrows on the curve. So you need to go back when you're graphing parametric equations, you need to add those arrows to your curve that basically show the direction that time is moving, or the angle. Okay, so you're getting like an orientation for which way your graph is moving. And the number of arrows, you know, just space them out evenly at different points in your graph so we can tell the direction that it's going. Okay, so let's do an example. Sketch the curve given by the parametric equations. X equals t squared plus 5, y equals t divided by 2 plus 4, and then negative 4 is less than or equal to t is less than or equal to 4. I'll show you on a later slide like another method we could use to graph, but a most basic method for graphing parametric equations is create a table of values, but instead of just an xy table, you're going to need txy. So I'm going to create a txy. Now, some parametric equations will come with a restriction for t. So like a restriction to your domain, negative 4 is less than or equal to t is less than or equal to 4. So we should only plug values between negative 4 and 4 in for t. If the parametric equation does not come with that statement, then you can choose what values for t you want to plug into the equation, but you'll have to look at both your equations because sometimes you can't plug every number into an equation. Okay, there are restrictions to different functions based on their domains. Okay, so here I want to go from negative 4 to 4. And in my table, note that I don't necessarily have to put every single number from negative 4 to 4. Like I need a sampling of points so I could get a good idea of what my graph looks like. So I'm just going to go by 2's. And I'm also looking at my functions. That's going to work out pretty nicely when I plug into y, because I have to divide my t value by 2. So if I choose even values, that will just make my math a little bit easier. Now, once you choose your t values, you just got to plug them in for x, and then you got to plug them back in for y. Okay, so I'm going to start with all my x's. T squared plus 5. Negative 4 squared plus 5 is 16 plus 5, or 21. Negative 2 squared plus 5 is 4 plus 5, or 9. 0 squared plus 5, 2 squared plus 5, and 4 squared plus 5. when I do my y column, remember y is a function of t, so you're putting the t values in for y, not the x values. And so again, I just have to do -4 divided by 2 is -2, plus 4 is 2. -2 divided by 2 is -1, plus 4 is 3. 0 divided by 2 plus 4 is 4, 5, and 6. When you look at the column for x and y, the values in the table are kind of representative of the type of function that they are in terms of t. Like y is really just a linear function of t with a slope of 1/2. So we don't see that slope because we're going by 2's over here, but if I put -3, that t value would have been 2 plus 5, or 2.5, 3 and 3.5, so I can see that. And then this one is quadratic again, so you know about quadratic equations. They are parabolas, they're U-shaped, so we can see how we start high at 21, we come down to our vertex, and then we turn around. Okay, so those tables are even representative of those functions as t. Okay, after that, I'm going to graph my parametric equation. So I need to make a Cartesian coordinate plane, which has only x and y. So when you're graphing, you're not really focused on the t in terms of actually graphing the points. You're going to focus only on x and y. And I notice for my x's that I have to go from 5 to 21. So I'm going to make my horizontal axis a little bit longer. Okay, and then my vertical axis here. So this is my vertical x and this is my horizontal y. I'm going to go by 1s on my vertical axis. And then I'm going to go by 5s on my horizontal axis. I don't really need to label every single point there. So I would just say, like, draw a graph big enough on your homework, whether you're using graph paper or not. I don't think that that's really necessary, but so that you get an accurate shape, like scale things nicely, really think about your tables. And then just plot your points. So I'll give you a minute to kind of plot your points. These look about the same location as your points. Okay. And so draw your curve, which, obviously this is not a straight line, so I'm going to draw a curve. And then as you were plotting your points, keep a mental note from your parametric table over there. What were the directions that you plotted the points? Add in your arrows. When I check your graphs with parametric equations on your test next Wednesday, one of the things I look for is you have the arrows. You have the direction of your graph labeled. So I need to see that for parametric. Okay. Some of you may choose, if you want, you could label some of the t values. So if you wanted to say this was t equals -4, this was t equals 0, and this was t equals 4, you can add that in. But if you have the arrows there, then we know what order the time is going. What shape does that kind of look like? A sideways parabola. Okay, yeah. And so that's actually one shape that we're going to talk about in our next chapter, chapter 10a, parabolas that open left and right. Those are part of the conic section. Just so that you're aware, if you have a parabola that opens left or right, instead of being x squared, it would be a y squared parabola. So if you ever have a y squared, that would mean that you'd have a parabola that opens left or right as opposed to an x squared. Okay, so you'd have a regular x and then you'd have a y squared. Okay, now another task that you'll be asked to do, we're going to work with the same problem. Okay, another task that you'll be asked to do is, then, can you take a set of parametric equations and eliminate the parameter? So we want to eliminate the parameter here. Remember that the parameter is that extra variable, not x or y. It's usually time or angle, so t or theta. So we want to eliminate t. And if we eliminate t, we'll be writing this equation in its rectangular form. Rectangular form, which would be just x and y's. I'd like you to have just a quick little brainstorm at your table. Can anybody think of a way that we could work with those two equations together and eliminate the parameter t? So just kind of throw out some ideas. What do you think you could do to get rid of t, if anything? See if anybody's got any good ideas.
It's like solving.
Okay, sounds like there were a few discussions. Any ideas? Solve for t. In which equation?
Could you do it in both or either?
Could you do it in both or either? Yeah, I'd say so. I'd say this. Solve for t in one equation. Okay, so that would be my first step. Solve for t in one equation. Now, does it matter which equation you choose? No. Which one do you want to solve for t? I heard the first one, x. So we're going to solve for t in x. X equals t squared plus 5. To get t all by itself, I would first have to subtract 5. And then I would have to square root both sides. Now you'll have to be careful here in parametric equations. If you square root to solve, we have to add that plus or minus because we're thinking rectangular things. So we'd have to say it could be plus or minus the square root of x minus 5. Okay, that's fine. And then our second step would be if you only solve for t in one equation, sub that expression in for t in the other. So it's a lot like when you think back to Algebra 1, solving systems of equations. How many equations are in a system? 2 or more. And one of your methods is basically substitution, where you try to have like a y equals or an x equals, and you substitute it into the other equation. Okay. So that's basically what we're doing right here. So I would write y equals plus or minus the square root of x minus 5 all over 2 plus 4. And this would be fine. I'm going to rearrange it just a little bit. And I'm going to say that like if I'm dividing all of that by 2, aren't I really just multiplying it by 1/2? Okay, so I'm going to write it as y equals plus or minus 1/2 square root x minus 4 plus, or sorry, x minus 5 plus 4. Oh, I like this a lot. Because what this tells me, and think back to Algebra 2 and also first semester in pre-calc, this should be a square root graph, which I could imagine in my head. A square root graph is sort of this shape right here. It's got a plus or a minus, so then that includes the reflected shape, so that gives us that sideways parabola, right? And it's going right 5 and up 4. Let me flip back to my other slide, and you can look at your graph. You can see here's the positive square root on the top. Here's the negative square root function on the bottom. Have both of those square root functions been moved right 5 and up 4? Yeah. And then they have like a vertical shrink of 1/2.
I thought you couldn't have a negative polynomial. Start with square root graphs because you can't square root a number of things.
You cannot have, yes, that's an issue we'll have to address. Oops, I went the wrong way. You can have negative y values, but what cannot be negative is what's underneath the radical, right? Like you can't take the square root of a negative number. So then this is going to affect the domain. And like also think about the fact that up here we had limited our t. Okay. We're going to have to limit our x. So what's the lowest value of x we could put into this? 5. So I would add on to this, like we should have a domain that says 5 is less than or equal to x, which is less than or equal to whatever my highest value of x is from my largest value of t. So you could see that. I'm going to actually flip back here. Here's my minimum for x. Here's my maximum for x. Like, and those are cut off. If it just said where t is greater than or equal to 4, I would just have to say where I have to be greater than or equal to 5. But now I have to cut it off at 21. So I would close it at 21 too. Okay, great. Does anybody have any questions about anything there? Okay, try this one. X equals t minus 2, y equals square root t minus 6. I see a lot of people as I walk around the room, go ahead and start with the TXY table. I think that's great. This one's a little bit different because there was no specifics for t, so you had to choose your own t. Notice that in my table, my lowest value of t is 0. Why is that? Yeah, you've got the square root of t, so the lowest value for t in the parameter for y, or the equation for y, t must be greater than or equal to 0. So it wouldn't really make sense to put anything in for like, negative value, because you're not going to get a y value out and you'll have nothing to graph. So use the domains of your functions that are creating your parametric equations to figure out what kinds of values for t you put in. And then I chose special values for t that would be easy for me to calculate, right? So I chose only numbers that I could take the square root of. Do you have to do that? No. Could you have used 0, 1, 2, 3, 4? Yes, you would have some decimals. That's okay. And we're going to come up with the same graph. So it doesn't matter how you choose to do that. I'm going to go ahead and create my graph. And plot my points. And remember, I'm really only plotting my x and my y. So I'm doing -2, 6. -1, 7, 2, 8, and if, oh, I didn't go out very far. If I went out to 7, then I would be at 9. So when I draw my curve, I really just have this curve, and as I plotted my points, I put in my orientation. Maybe put that up. I don't mind if you're doing other things. Keep yourself busy. Little rough up there on the board, but what shape is that? It's another square root. It's half the parabola. It's a square root function. I saw a few people start by eliminating the parameters. So they wrote t equals x plus 2, and then they're going to sub that in for y. Y equals the square root of x plus 2 plus 6. Is that a square root that has been shifted left 2 and up 6? Yeah. So they could have graphed from the rectangular equation. Note that that's a shortcut you can use, and I'll use it on our next example. But the only thing you'd have to do then is figure out like what orientation your points are going. So like what orientation or direction for your arrows you want. So you might still have to do a couple of values in the parametric table. Okay, and that would be okay. Does anybody have any questions here? If I were writing this, I might also say x is greater than or equal to 0, just to clarify. But that's kind of implied in the square root. Sorry, -2. It's kind of implied in the square root function. Okay, one more example really quickly with this graphing piece. And this is one where I'm going to show you how like I would graph this one by eliminating the parameters first. Wouldn't have to, but what I notice about this one is my y equation is a fraction, and that means that I'm probably going to end up with a rational function in rectangular form. Rational functions are those functions we talked about in first semester where you have like vertical and horizontal asymptotes, and they're usually like broken up into different pieces of a graph. So I would actually prefer myself to graph this not with points, because I might need more points in order to graph it if I'm just doing the like TXY table. So I'm going to choose to write it in rectangular form first. And then you'll see an example like this, and you can kind of take your pick on your homework what method you're going to use. So I would solve for t in the first equation and get t equals x plus 1. I would plug that t into my y equation, and I end up with x plus 1 over x. And this is the rectangular function that I would graph. So when I'm graphing it, I know that my denominator x, if I set that equal to 0, that's my vertical asymptote. So in this one, x cannot be 0. There's my vertical asymptote. To do my horizontal asymptote, I have to check the degrees of my numerator and my denominator. So the degree of my numerator is 1, the degree of my denominator is 1. When they have the same degree, the horizontal asymptote is the ratio of the leading coefficients. So that would be like 1 over 1, which is just y equals 1. So I'm going to put my horizontal asymptote at y equals 1. Maybe I'll label these things. And then if you think back to first semester, you can really quickly find a point on your rational function graph. If you have a value in the numerator, set it equal to 0, and that will be your x-intercept. So x plus 1 equals 0. My x-intercept is at -1. So I cross the x-axis at -1. And then I know that I'm going to get those two branches of a rational function capped between my asymptotes. So good reminder of things that you did in Algebra 2 and first semester pre-calc. And to me, that's a lot quicker using the asymptotes and like an extra point than having to do like a TXY table and like finding out that you have these like weird issues with your graph, like what is my graph doing, right? The only thing that's now missing from my graph though are my arrows for direction. So in order to find my arrows for direction, I would just real quickly set up a TXY table, and you really just need to do like 2 points, because then you'll know what direction it's moving. So I noticed that in my parametric equation, t cannot equal 1, because it makes my denominator equal 0. So I'm going to choose -1 and 0, and just plug those in. When I plug it in for x, -1 minus 1 is -2, 0 minus 1 is -1. And then plug those values in for y. -1 over -1 minus 1 is -2, so -1 over -2 is +1/2. And then 0 over 0 minus 1 is just going to be 0. And so I'm seeing the progression from t. I'd be going from this point at -2 1/2 to the point -1 0. So my arrows should be going something from left to right. It is possible for your arrows to move from right to left, so you just have to be careful and check to make sure that that's correct. That would be like a sign issue. Any questions on how I approached that one? I know for sure on your homework there is one rational function, so I would maybe employ that method to graph that. Okay, the next thing I want to talk about really quickly, just so that you have like seen this, because really these follow very nicely from the first part of the chapter, which we haven't done yet. So just so you're not like, huh, what's this? I've never seen this before. We'll do one with a sine and a cosine. So this says sketch the graph given by the parametric equations. X equals 2 cosine theta, y equals 5 sine theta. Note that when we use theta, the angle for our parametric equations, we're still in terms of x and y. This is section 10.6, so we haven't even introduced polar coordinates at this point. So like we're not doing any of that polar work that we did at the beginning part of this chapter. We're sticking only with x, y. Theta is just our third variable. If I were doing this, I would start with a table, theta, x, and y. And then, this works out really nicely if you kind of use the graphing method that you use for the limosome, which is just figure out what those values on the quadrantal angles are as you go around. So like 0, pi over 2, pi, 3 pi over 2. And you could put 2 pi on the list, but we know it's coterminal with 0, so it's going to get us right back to that first point. And then we just have to run through what is the value of x. If you need to, remember we kind of talked about this yesterday when we were going over stuff, I think. You guys were in my class that got shortchanged though, so maybe we did it. If you have trouble doing sine and cosine correctly, you could always just draw this little image from the unit circle, and then you'll maybe get more accurate answers when you're doing it. So, I'm going to start with 0. 2 times cosine 0, the cosine of 0 is 1, so that's 2 times 1 or 2. 2 times cosine of pi over 2, that's 2 times 0 or 0. 2 times cosine of pi, the cosine of pi is -1, so -2. And 2 times cosine 3 pi over 2, so 2 times 0 is 0. Go to your y's. 5 times sine of 0, the sine of 0 is 0, so 0. 5 times sine of pi over 2, that's 1, so 5 times 1 is 5. 0 and -5. Plot those points. 2, 0, 0, 5, negative 2, 0, 0, negative 5. And then, just like before when we were graphing polar curves, they are not like connect the dots, so it's not going to be a diamond. It should be round and more like an oval. And I know the direction of my shape, something like this. Does anybody know the mathematical name for this shape? Not a circle? Oval is the normal, like the regular name. Mathematical name? An ellipse. You probably heard, like, if you ever studied in science, like in space, like elliptical orbits. Okay, they're orbits that are not perfectly circular. From gravitational force, so it's an ellipse. So just kind of be aware that if you get to a parametric equation that has sine and cosine, it's probably going to be like a round shape, like an ellipse. It could be a circle. Okay. So it'll be one of those round shapes. And the final thing that I need to show you just really quickly is, how do you change this into XY equation, rectangular equation? So we just need to eliminate the parameter. Okay, so it's the same set of equations for the parametric. X equals 2 cosine theta, y equals 5 sine theta. And the issue here is if you think about like solving for the parameter theta in one of the equations, it doesn't work out quite as nicely because like you'd have to, like in x, divide by 2, and then what, you take the inverse cosine of x over 2, but you can't evaluate that because there's a variable and you're supposed to plug that into the other equation. Not nice, right? Okay. So what we're going to do is we're going to use one of our identities from chapter 5, which says that the cosine squared theta plus sine squared theta is equal to 1. We're going to use our Pythagorean identity from chapter 5. And in order to plug into that Pythagorean identity, all we have to do is solve for sine and cosine, which is very easy. In this first equation, to get cosine all by itself, I just have to divide both sides by 2. So cosine is x over 2. In the second equation, sine is y over 5. Then, where you see cosine in the Pythagorean identity, put x over 2. Where you see sine, put y over 5. Equals 1. And the last thing I would do is just square the numerator and the denominator. So x squared over 4 plus y squared over 25 equals 1. That's your equation. This is the standard form equation for an ellipse, x squared over a squared plus y squared over b squared equals 1. And we're going to see this quite a bit after our test when we start chapter 10a. We're going to be doing conic sections, so we'll be looking at that formula. So you don't necessarily have to know that, but it's just the connection that when we see it again next chapter, you'll be like, oh yeah, we have seen that, and we graph those round shapes, those ellipses. If it's a circle, they'll have the same number in the denominator. And so do like x squared over 25 plus y squared over 25 equals 1, which you could then multiply both sides by 25 and get x squared plus y squared equals 25, which looks like the equation of a circle. Okay, here is your homework assignment. You have some required problems. Please make sure that you work on those. Your Chapter 10B test is next Wednesday. It will be calculator and no calculator. Parametrics should be on the calculator portion, I believe, versus like the graphing Lie-Mousson, rose curve, etc. Those are going to be in the non-calculator. And I'm also going to put here, quiz is due tomorrow. Don't get late points.